Science is simply common sense at its best, that is, rigidly accurate in observation and merciless to fallacy in logic. This is Thomas Huxley. Indeed, strong observational skills and its dogged application quite holds the key to intuitive insights into the foundations of just about everything. Understanding the derivative of functions, at least the parent functions, is highly intuitive, and derivative of most functions may be intuitively appreciated and analyzed. Anyways, conceptual soundness is best enjoyed and deployed in its intuitive rendering, its mental imagery. We will intuitively explore the exact nature of the derivatives of x squared, and we will not use any numerical methods. That would be too easy and carry little conceptual gains. We will use their graphs for defining the exact nature of behavior of the graphs of their derivative functions of functions. However, to keep it broad and easy, we should seek the parent function of the derivative function rather than the exact derivative function. We will seek the parent function of the derivative of x squared, and that would give us the exact nature of the derivative function. Further, recall that the derivative of a function is also a function. This is to say that the derivative is not a value, but a function. And that implies the derivative will have all the characteristics of a function, such as a characteristic set of slope values. Let us get firm-footed about the basics needed for intuitive appreciation of derivatives. First, derivative of a function at a point is the slope of the tangent at that point, slope being the rate of change of the values of the function. Second, talking of tangent at a point implies we are talking about tangents to the graph or the curve of the function. Third, the slope of a tangent has two attributes, magnitude and direction. By direction, we mean increasing or decreasing functions. The picture shows that the magnitude of the slope of the line is increasing. For each change in the x-coordinate values, the y-coordinate value is increasing in greater amounts as compared to the increase in the values of x. This picture shows the slope of three lines, decreasing, unchanging, and increasing. In decreasing slope, for the increase in x-coordinate value, say from -3 to -1, the y-coordinate values are decreasing from 6 to 2. Fourth, the direction of rate of change, that is, the derivative of a function at a point, is the same as the direction of the change of the function itself. This is a very significant appreciation of the relationship between the derivative direction and the function direction at a point. And this is at the core of the intuitive appreciation of the derivative of a function at a point. It is not to say that the magnitude of change in the function or the corresponding magnitude of the rate of change of a function is of less value, but it is kind of secondary to the nature of direction. The takeaway is that using the direction of the function, we get the sense of the derivative function shape. To be precise, the shape of the parent function to which the derivative function belongs. Fifth, what does the magnitude of the slope of the function at a point say about its derivative at that point? It is all too obvious. The fast-changing function outcome around a point implies a higher magnitude rate of change around that point. Graphically, it means sharply rising curve. Curve getting closer towards the y-axis as x, the independent variable, increases. This picture shows a curve that is slowly or not sharply rising. A straight line with similar slope is also shown. This shows a curve that is steadily or moderately rising. A straight line with similar slope is also shown. This shows a curve that is rapidly or sharply rising. A straight line with similar slope is also shown. We fine-tune the possibilities in the shape by using the magnitude dimension. We will use this knowledge of direction and magnitude of change in function around a point to get the nature of its derivative function. Specifically, the direction of change of a function at different points will help us get a sense of nature of the curve that represents the rate of change of the function at those points. The direction of the change of the function and the rate of change of the function is the same. After all, a decreasing function at a point will have a negative rate of change. The magnitude of the change in a function around a point gives the exact amount of increase or decrease in the rate of change around the point. Thus, the knowledge of the magnitude of change of a function tells us about the gross nature of the magnitude of its rate of change around that point. Let us consider the parent function fx equal to x squared. Graphically, it is a parabola. All graphs in this family are parabolic, with different vertices. Expectedly, to get to the nature of the derivative function of x squared, the first step has to be study of the behavior of the slope of the function at different points. That is, the slope, the curve of the function at different points. We will look at the slope to know its direction and magnitude at various points. And the second step is to use the knowledge of the slope to construct a curve, that is, the derivative curve that shows the expected behavior of the direction and magnitude of the rate of change. For the x square curve, we will study the direction of the slope at origin and in the first and in the second quadrants. And once we have figured out the direction, we will use the magnitude of the slope to fine-tune the nature of the rate of change or the derivative function's curve. Before we explore the x square curve, let us revisit the properties of slopes. It would tremendously help ahead. Observe the picture. When a tangent to a curve that gives the slope of the curve at a point is such that it makes an obtuse angle with the horizontal, that is the x-axis so to say, in the anti-clockwise direction, the slope at that point is negative. Or, when a tangent is tending downward while moving from left to right on a graph, the slope of the line or the curve is negative. This reflects the fact that the output value of the function, the y-axis value, decreases as the independent variable, or the input x, increases. Observe the picture. Expectedly, when the line or the tangent is making an acute angle with the horizontal in the anti-clockwise direction, the slope will be positive. This picture shows the other condition. When the tangent to a curve is parallel or horizontal to the x-axis, then there is no change in the value of the function at the point where the tangent touches the curve. Hence, the rate of change of the function is 0, and thus the slope of the function is 0 when the tangent is parallel to x-axis. Next, let us apply this understanding of slope to the curve of x squared. Broadly, we can observe the following in the graph of f(x) equal to x squared. First, for negative values of x, in the second quadrant, the slope of the given function is negative. The value of the function, the y-axis values, are decreasing as the x-axis values increase when we move from left to right along the x-axis. Recall, -4 is less than -2. Second, for positive value of x, the slope of the tangents is positive. That is, if x increases, the y values increase too. Third, the slope is 0 at x equal to 0, where the tangent is horizontal to the x-axis. In fact, it coincides with the x-axis. And we must expect a similar behavior from the rate of change of the function at x equals 0 and negative and positive values of x. Based on the observed behavior of slope of the curve of x squared, two imperatives emerge for the derivative function of x squared. And before that, let us reinforce that the derivative function is the values of the slope of the function. The first imperative is that the derivative function must pass through the origin, since at x equal to 0, the slope is 0. The rate of change of the function is 0 at x equal to 0. The second imperative is that the values of slopes are increasing for x greater than 0 and decreasing for x less than 0. Importantly, this suggests that the derivative graph could be any of the ones shown in the picture. fx equal to x, fx equal to x cubed, and fx equal to x raised to the power 5. All the three are parent functions and broadly display the aforementioned two imperatives. Of course, using the parent functions implies that we are talking about a broad category of input-output behavior. Yet, the parent functions are good enough to intuitively know the nature of the derivative function. We will next figure out the curve that best represents the derivative function by using the magnitude values of the slope. Now, we will use the values of the function around a point to know the magnitude of change of the function and thus the magnitude of the rate of change of the function around that point. The derivative curve will be steeper, more towards the y-axis, if the change in the values of the functions are more around a point. We will choose more than one point if need be to know the exact shape of the derivative curve. Let us study how the function behaves around the point x equal to 1. At x equal to 1, fx is 1. At x equal to 0.9, fx is 0.81. And at x equal to 1.1, fx is 1.2, 1. The function values 0.8, 1, 1, and 1.2, 1 are not far away from each other. This indicates that the fx values, the function or its output values, are not changing very sharply around x equal to 1. And graphically, it implies that x cubed, or x to the power 5, are not the graphs of the derivative function around x equal to 1. We can see from the graphs of x cubed and x raised to the power 5 that these have function values changing very sharply around x equal to 1. That is, the derivative function cannot be a curve such as x cubed or x to the power 5, wherein for a small change in x we have a large change in the value of the function, the y-axis. This suggests a straight line as a derivative for x squared. Fx equal to x is the best of the three curves to represent the derivative function of x squared. However, if we only know that the derivative function belongs to the family of the parent function fx equal to x, then we should know that there are infinite possibilities of the exact function of derivative of x squared within the family of fx equal to x. To be true, to get to the exact function that is the derivative function of x squared, we have to use the computational methods, but that is not conceptually and visually enriching, and we are not interested in it here. The takeaway from the derivative graphs in the picture is that the derivative of all quadratic functions is a linear function. We have logically derived the nature of the derivative function of a quadratic function. We really know what a derivative is, how it is derived, and what is it all about. For now, let us generalize that the derivative of all quadratic functions is a linear function, and for x squared, the exact derivative is 2x. To some, the values of the derivative function of a function is the values of the slope of the function at all points on it. The direction of the slope of a function at all points is also the direction of its derivative function, or the rate of change function, at all points on it. The magnitude of the change of function values around a point do indicate the possibilities of the magnitude of the rate of change around the point. For example, the magnitude of the rate of change cannot be big if the magnitude of change of a function itself is small. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.